Welcome, and thank you for joining this webinar, Advancing Quantum Communication, Role, Impact, and Technical Foundations of Quantum Technologies in 6G and Beyond, prepared by Alpert Research Team. Quantum communication is transitioning from academic theory to strategic infrastructure. This webinar explains how physics, not math, can guarantee trust, and how quantum systems integrate realistically into modern communication networks.
The pioneering quantum application, quantum key distribution, or QKD.
QKD's core purpose is not to transmit your user data. Its sole function is to generate and distribute a highly secure, secret cryptographic key.
Once that key is distributed and verified as secure,
Then Alice and Bob use it with a classical cipher like AES or even the theoretically unbreakable one-time pad to transmit the actual sensitive user data over a normal channel. QKD fundamentally shifts the entire security model
away from computational hardness.
It relies on the unbreakable laws of quantum physics. We're transitioning from what you could call assumption-based security to what is known as information theoretically secure keys.
And what does that mean? Information theoretically secure.
It means the security holds true even against an adversary who has infinite computing power.
You know, this idea of information theoretic security, it really brings us back to the ultimate gold standard of encryption, the one-time pad.
The OTP.
If QKD's only job is key distribution, it sounds like it's designed to finally make the one-time pad.
The OTP is mathematically proven to be unbreakable, but only if three conditions are met. The key has to be truly random, it has to be as long as the message, and critically, it must be used only once.
And the historic failure of the OTP wasn't the math, it was the logistics.
Always. How do you securely generate and transport a massive single-use key to someone thousands of miles away?
Let's transition now to the core technology that makes this possible, the QKD protocols themselves. And as we said, its singular purpose is generating and distributing keys. It's not for sending the actual user data.
And the protocols are broadly split into two camps. The first and most foundational are the prepare and measure protocols.
And the cornerstone there is BB84.
Bennett and Broussard, 1984.
Can you walk us through?
Think of it in four stages. First, Alice prepares the quantum states. She has two bases. Think of them like two different sets of filters. One might be horizontal and vertical, the other might be diagonal. For each photon she sends, she randomly chooses one of those two bases to encode a 0 or a 1.
Okay, so she sends a stream of photons, each randomly encoded, then they travel to Bob.
Right, now Bob has to measure them. He has the same two sets of filters, the same two bases as Alice, but he has no idea which one she used for any given photon.
So he just has to guess.
He randomly chooses one of his two bases to measure each photon as it arrives.
If his basis choice matches Alice's, he gets the right answer. If it doesn't,
The outcome is completely random. He has a 50-50 chance of getting it right.
so after the transmission, they have to figure out where they matched up.
That's the next stage, called sifting. Alice and Bob get on that public classical channel, and they only do one thing. They announce which basis they used for each photon, not the result, just the basis.
And they discard all the results where their bases didn't align.
What's left, the bits where they happen to choose the same basis, that forms their raw key.
And finally, they check for Eve.
The eavesdropping detection. They sacrifice a small portion of that raw key and compare it publicly. If Eve was intercepting the photons, her own random measurements would have introduced errors. If those errors push the QBE above the threshold.
They know they've been compromised, and they abort.
And abort. That's BB84 in a nutshell.
The sources mention a few other prepare and measure protocols. Six-state protocol, SAR-04, CowW. We don't need to go through all of them. What problem are they trying to solve that BB84 doesn't?
They're mostly about solving practical engineering challenges. For example, some protocols are designed to be more tolerant of noise in the fiber, or they work with cheaper, less perfect photon sources, things that make it more viable for, say, a metro area network. The six-state protocol, for instance, uses 3 bases instead of 2, which theoretically makes it even harder for an eavesdropper to hide. They're all variations on a theme, usually aimed at better performance or lower cost.
What about the second major category, entanglement-based QKD?
It shifts from Alice preparing states to Alice and Bob sharing a pre-existing resource,
Entanglement.
maximally entangled quantum states. Imagine you have two particles that are perfectly linked no matter how far apart they are. They exist as a single quantum system, a Bell pair. If you measure one and find it's a 0, you instantly know the other one is also a 0, assuming you measure in the same basis.
So the physics itself guarantees the correlation.
The correlation is the resource. In a protocol like E91, a central source creates these entangled pairs and sends one particle to Alice and one to Bob. They each independently and randomly choose a basis and measure their particle.
And then they compare notes on the bases they used, just like in BB84.
And because they know the correlation should be perfect, any attempt by Eve to measure one of the particles in transit would break that delicate entanglement.
And that would be immediately detectable as errors when they compare the results. Whether it's prepare and measure or entanglement-based, once you have that raw key, the job isn't done. You have to do key post-processing.
Right. First up is error correction.
Because even without an eavesdropper, the real world is noisy.
The fiber channel has losses, the detectors aren't perfect. So Alice and Bob use public protocols to find and fix the small, unavoidable discrepancies in their raw keys. They have to do this cleverly, of course, without revealing the actual key bits.
And after that, there's privacy amplification.
The idea is that through all this public communication, the sifting, the error correction, a very clever eavesdropper might have gained a tiny partial amount of information about the key. Privacy amplification takes the corrected key and mathematically shortens it using a strong hash function. This process effectively squeezes out any partial information Eve might have, resulting in a shorter but perfectly secret final key. The message is crystal clear. The integration of quantum systems into our network architecture is happening now, not in some distant theoretical future. We've established that quantum communication will not replace classical wireless networks, but it will redefine how trust, security, and optimization are built into 5G advanced and 6G systems.
Interested in gaining a deeper understanding of the transformative power of wireless technology? Join the Alpert Research Team's webinars to explore cutting-edge wireless innovations, their applications, and their implications. Click the links below to learn more.